Example 4. A pendulum bob attached to the ceiling of a train moving at a speed of 80 km per hour. As the train made a turn at constant speed, an observer looking from the back of the train saw the pendulum tilt as follows. Okay, so in this diagram we can see that this is the roof of the train. You can try this experiment also, either in the bus or in a train. Okay, so what you need to do is you take a string. Okay, at the end of it, right, maybe you can use plasticine or blue tack, roll it into the ball, so that will be your pendulum bob. Then at the other end of the string, maybe you can stick a tape or blue tack and stick it to the roof of the train or the bus. So if the train starts to turn, you will be able to see something similar to this. Okay, the pendulum bob will not remain in a vertical line but will be tilted at an angle. So when the train made a turn, line number 2, we know that it's going round in part of a circle. Okay, it need not be going round in a complete circle. As long as it is making a turn, it is part of a circular motion, we can use circular motion concept, okay, at the instant when the train is turning. So how do we find the radius of the turn? Well, to find the radius of the turn, I need to have some information, probably about the force. So to start off with, if you're not too sure what to do for mechanics questions, always start with free body diagram. Okay, consider the free body diagram for the pendulum. The pendulum bob is attached to the string, so there will be a contact force, which is the tension, and then there will be a weight, mg. Okay, at the instant shown, you're told that the pendulum is tilted at an angle 40 degrees to the vertical. So resolving forces vertically, we know that the vertical forces, which is your mg, it must be equals to t cosine 40. Okay, at this instant the angle is fixed at 40, so it must be in vertical equilibrium. Okay, horizontally, there's only one component of force from the tension T. So we have T sine 40, and there is no other force to balance off this T sine 40. And this have to be the case because the train is making a turn. So there must be an unbalanced force. So the T sine 40 will be the horizontal unbalanced force, which actually provide the resultant force for the circular motion. So we equate T sine 40, which is the resultant force here, to be equals to the centripetal force, mv squared over r. Okay, to find the radius, you can take equation 2 divided by 1. Tension will cancel off, so I will get tangent 40 to be equal to v squared over rg. Velocity is given 80 km per hour, so you need to convert that to meter per second and substitute into the equation. You should get the radius to be 60 meters. So that is the radius of the train when it's making a turn. Okay, so it forms part of a circle with a radius of 60 meters. And the pendulum bob is inside the train, so it will also undergo the same circular motion as the train. So the radius of the circular path of the pendulum bob is also 60 meters. Okay, in B, you're asked to deduce the direction. Okay, notice from our calculation here, right, when we resolve the forces, there is a resultant force that is given by T sine 40. So the resultant force is to the right. And we know that the resultant force is a centripetal force, must always act towards the center of the circle. So the train must be turning right, because the center of the circle is to the right, since the centripetal force is to the right.